Thank you, Wong. My name is Jason Jabbour, and I'm also working on the bifurcations in the construction of elastic Mobius bands project from Cornell with Dr. Borum, Ujia, and my research partner, Wong. So Wong went a little bit into the background of our problem, and then he basically showed you how as you specify finite values for bending and twisting stiffnesses C1 and C3, and you begin to twist a three-dimensional rod into a Mobius band, you'll reach points of instability. Today, I will be looking into what happens at these points of instabilities, specifically for bending stiffnesses uh, of infinite value. Okay, but before I can do that, let me quickly recap our problem. And we can basically describe a three-dimensional elastic rod with the following geometric optimal control problem. And as Wong showed you, we start our rod in the shape of a circular ring, and then we start twisting our rod from 0 to 180 degrees. Somewhere along the line, our rod will become unstable. And at that angle, we can call this angle the critical twist angle, where a rod becomes unstable. Okay, so now we can expand a little bit about what Wong was speaking about in his presentation, and we can ask the following question. We can say, what is the value of the critical twist angle when C3 is infinite? Now, why am I asking this question? What's my motivation behind asking this question? Well, C3 is the bending stiffness, and if C3 is infinite, then our rod can only bend in one direction. In the future, we hope to analyze Mobius bands as two-dimensional surfaces. Two-dimensional surfaces can only bend in one direction, so we can approximate this in our problem by setting C3 to be infinite. Okay, so let's start analyzing this question, and we can do so by setting C3 to be infinity, checking different values of C1, and testing when our rod becomes unstable. When we do so, we'll see this graph where we have our twisting angle versus our twisting stiffness, C1. Let's say we start at a twisting stiffness of 1 and a twist angle of 0. We can check if our rod is stable or unstable. If it's stable, we'll plot this blue point and then start to increment our twisting angle until we reach our first unstable point, denoted by this red dot. When we reach this first unstable point, we can then increment our twisting stiffness and repeat this process until we see this relationship where as stiffness increases, the angle at which our rod becomes unstable exponentially decays. I'd also like to point out that for the initial few values of our twisting stiffness, our rod always becomes unstable at 180 degrees. So we'll keep this in mind as we continue analyzing a problem. But as the twisting angle increases, we reach these points of instability. And now we can ask what type of bifurcations happen at these points. In order to analyze this, we can set a specific twisting stiffness value. Let's say C1 is equal to 5, and we begin to twist our rod from 0 to 180 degrees. As we do so, we'll check if our rod is stable or unstable. And we can represent solutions by the points mu1, mu2, and mu3. If you recall from Wong's presentation, mu was a function that we solved for to find equilibrium shapes. So we will use the initial condition from mu to represent solutions as points in the space mu1, mu2, and mu3. Mu has 6 components, but for visualization purposes, we're only going to look at the first 3. Okay, so as we're twisting our rod from 0 to 180 degrees, we might see an unstable point, right? And if we do, we can then perturb our initial condition mu by this eigenvector v that we get from the singular value decomposition of our matrix J, and this perturbation amount we can call epsilon. What am I trying to say here? Well, basically, I'm trying to jump onto these branches, branch 2 and branch 3. And if I'm successful at doing so, then I observe a pitchfork bifurcation. Okay, fair enough. So let's pick a twisting stiffness value. Let's say C1 is equal to 1, and let's check if we actually see this. I will show you an animation, so bear with me if this doesn't make complete sense initially. But what we're doing here is we're setting our C1 value to 1, and we're twisting our rod from 0 degrees to 180 degrees. And actually, we don't see this pitchfork bifurcation like I was talking about. And that's because we reach our first unstable point at 180 degrees. But we can still learn something from this. And that is, at 180 degrees, we have a Mobius band, which is a closed surface. So if I rotate this surface around, keeping the origin fixed, then I get a continuum of points. These continuum of points satisfy my boundary conditions. So, and then I can plot these points using as this purple curve. And every point on this curve is the same shape of the Mobius band, it's just rotated around. So here's the animation that I promised I would show you. And what we're doing is twisting from 0 to 180 degrees. When we reach our Mobius band at 180 degrees, we move along this purple curve, and you can see that the shape of the Mobius band remains the same, it's just being rotated around. Okay, well, it wasn't completely unexpected that we wouldn't see this pitchfork bifurcation for a stiffness value of 1, because we actually knew that we would reach our unstable point at 180 degrees. So now let's actually increase our twisting stiffness. Let's say we use a stiffness value of 5, and I promise I have no more tricks up my sleeve this time. And this is what we get. We're starting from 0 degrees, twisting up to 180 degrees, and somewhere along the line, we will reach this first unstable point. And the entire branch after this unstable point is unstable. We also can find these left and right branches, which are stable branches, meaning this is a supercritical pitchfork bifurcation. This result's consistent for different values of C1. So here I have C1 is equal to 5, 15, and 50, all of which show this supercritical pitchfork bifurcation. Now I can investigate if all of these branches lead to the same shape of the Mobius band and it's just being rotated around. I can do this by plotting that purple curve that I showed you in the previous figure, our continuum of solutions. If all of these branches lead to the same continuum of solutions, the same mu of t, then we know that they lead to the same shape of the Mobius band. And this is precisely what's happening. All 3 branches touch the same continuum of points, meaning that they lead to the same shape of the Mobius band, it's just being rotated around a little bit. To clarify, this is what we're doing. So we start at 0 degrees and increase up to 180 degrees. Somewhere along the line, we'll reach our first unstable point, pick a stable branch, and then as we move along our continuum of solutions, you can see that our Mobius band shape remains the same, it's just being rotated around. Okay, well, I showed you a case where we reach our first unstable point at 180 degrees. And I also showed you a case where we reach our first unstable point before 180 degrees. But how does this plot on the left deform into this plot on the right? I can visualize this by slowly incrementing my C1 value. So here I'm starting at a twisting stiffness of 1, and I'm incrementing by a fourth. And you can see that the curves begin to overlap. When they overlap, we start seeing this pitchfork bifurcation. Okay, hopefully everything up to this point has been understandable. So let's look at what happens if we twist past 180 degrees. Here I'm going to select a twisting stiffness of 5, and I'm going to use these black marks to denote where we reach 180 degrees. And what we can see here is after 180 degrees, my left and right branches become unstable, and they remain unstable all the way up to 360 degrees. Also, we face this numerical issue where our middle branch keeps jumping onto our branch number 3. So we'll look into this a little bit later, but first let me show you what's happening here. We're twisting from 0 to 360 degrees. When we reach our first unstable point, we'll pick a stable branch. But after 180 degrees, our rod has no choice but to be unstable all the way up to 360 degrees, which is quite disappointing. But if you remember, we were facing this numerical issue with our middle branch. So let's try to fix this. And we can do this by starting our rod as a double ring at 360 degrees and untwisting from 360 degrees to 0 degrees. And what we actually see, we get this curve right? And a little portion of our curve is unstable. Where have I seen this little unstable portion, and where have I seen this shape at 180 degrees? Well, turns out that this curve that we got actually connects to the end of our middle branch where we previously were facing numerical issues. To clarify, this is the curve that we got from untwisting from that double ring, right? Starting at mu2 is equal to 4 pi over here. And it connects perfectly into the middle branch. So what happens now is that our rod can actually pick a stable branch, and then at 180 degrees, it'll jump down to the middle branch, which is stable all the way up to 360 degrees. Okay, so today I talked a little bit about the instabilities for infinite bending stiffnesses. In the future, we will continue to analyze what happens as we twist past 180 degrees. And now that we have the framework set for C3 being infinite, we can start to look at Mobius bands as two-dimensional surfaces. I'd also like to give a big thank you to Dr. Borum and Ugia for all the hard work they put into this program.